Okay, hello everyone, and welcome to another Tutte Colloquium. Today we're very lucky to have our very own David Zhao giving a talk. As most people here already know, David received his PhD from Harvard before joining Waterloo, I think around 2006. In addition to his academic work, he has various other affiliations. Like you see here, he's a chief cryptographer at Evolution Q. And this afternoon, he's going to be telling us about the problem landscape of SDIH. So please go ahead, David.
All right, it's SIDH, the I and D word.
SIDH.
Yeah. I'm not actually quite sure how to pronounce it. Some people say side, but I just say SIDH. So anyway, thanks for the introduction. Welcome. I'll be talking about the problem landscape of SIDH. Most of this work was done jointly with my former master's student, David Urbanek, who is now at Toronto. So to start with, I'm going to talk about what elliptic curves are. A lot of this stuff, probably most of the cryptographers know all this, but this is a Tutte Colloquium and has to be accessible to non-cryptographers. So an elliptic curve is a curve that looks like this, the equation that we have here on this slide. Y squared is equal to x cubed plus ax plus b. The reason why elliptic curves are interesting is because they have lots of mathematical structure, right? So they are algebraic curves, right? As you can see, they're defined by polynomial equations. They have the structure of a group, right? You have a group law on elliptic curves. So here, I've drawn the group law here. The point P is this point over here that I'm darkening here, then the point Q, and the point P plus Q goes over here. So this is a group law. It can be defined using geometry, as I've shown on this slide. You can also define it algebraically so that it makes sense independently of geometry, which then lets you do this group law in all sorts of settings where you don't necessarily have geometry. If you do like other math, elliptic curves are schemes and sheaves and stacks and all sorts of crazy things that are much too complicated for our purposes. But there's a lot of math structure on them. They're very famously used to prove big theorems like Fermat's last theorem and things like that. Okay. So we'll be talking about elliptic curves today. Now, elliptic curves traditionally have been used for cryptography, but only in the most sort of basic sense, right? If you talk about elliptic curve cryptography in general, most of the time, what you mean in that case is you mean cryptography based on this group law, based on this arithmetic of points on elliptic curves, and that alone is enough to support, some very functional and rich cryptography. But what we're going to talk about is sort of beyond, just the basic group law. So we're going to talk about isogenies, which are maps between elliptic curves. And it turns out that using isogenies, you can do more in a sense, but it's in a very sort of precise sense, right? Like you can't, as far as I know, there's not like more functionality that you can do with isogenies than you can do without isogenies. Like for example, signatures you can do just as well with or without isogenies. But isogenies give you another way to do this. And I'll get into the motivation a little bit later. But one of the main reasons for wanting to do it in this different way is because isogenies are believed to be what we call quantum resistant or quantum secure, so that even if you have a quantum computer, you can't break the isogeny on crypto systems, whereas if you were just using normal elliptic curve crypto systems, you could break them. All right, so I'll start now with the definition of an isogeny. It's a very innocuous seeming sentence. An isogeny it's an algebraic map that is a group homomorphism. All right, and in a certain sense, this definition is even overkill. All you actually need is it would be equivalent to say that an isogeny is an algebraic map that sends the identity group element to the identity group element, right? And then it turns out from that, the homomorphism property follows. But it's equivalent, so I'll just use this definition. It's probably more representative of the actual properties that we care about. Okay, so the fact that it's a group homomorphism is not in and of itself, I think, too restrictive. Given any groups, and by the way, these are abelian groups because, as you can see, the order of P and Q doesn't matter when you add them. Like given any two abelian groups, there's probably a bunch of choices for group homomorphism between them, but what's really restrictive here is the requirement that this be an algebraic map. Okay, so it has to be defined by essentially polynomials, right? Although technically you're allowed to take quotients. So if you're quotients like fractions of polynomials, so really it's rational functions, right? But that's a very serious restriction that that requirement sort of makes the isogenies makes it so that isogenies need a lot of structure, right? You need a lot of sort of organized structure in order to have an isogeny in the first place. One of the ways that you can get that structure is if you go back to sort of first year group theory or something like that. When do people even take first year group theory? I don't know. But in first year group theory, you learn that when you have a group homomorphism, right, you have a concept of a kernel, which is the points that are annihilated by the homomorphism. And you also learn something called the first isomorphism theorem, which says that if you it's like, if you know the kernel and you also know that the homomorphism is surjective, then the homomorphism is uniquely determined by that information, more or less, right? So that there's essentially up to isomorphism only one surjective group homomorphism for any given kernel for any given subgroup of a group, being where the idea is that that subgroup has to form the kernel. Okay. And now, if your group is not abelian, you have to worry about normal subgroups. But here you don't. Group is abelian. So let G be any finite subgroup of E. It's actually important that G be finite here and the reason for that is because these isogenies, they are rational maps, right? So being, essentially they're polynomials, although we're taking quotients. But the idea is that a polynomial can only annihilate finitely many points, right? Unless it's the zero polynomial. A polynomial only has finitely many roots. Right, and it could be like a constant isogeny, but that's not very interesting, right? That would be the analog of a zero polynomial. So ignoring that possibility, a polynomial is only going to have finitely many roots, and so what that means is that by virtue of being algebraic, an isogeny can only have a finite kernel. There can only be finitely many points that are annihilated. And so what Veloux formulas tell us is they give us a way to go backwards, right? So that now, instead of starting with an isogeny and then taking the kernel, which is a finite subgroup, you now start with a finite subgroup and you say, all right, so which isogenies can you construct having this finite subgroup as a kernel, all right? And just as in group theory, where you have the first isomorphism theorem that tells you, in essence, the answer is only one, right? So here, in essence, the answer is only one. There's exactly one isogeny up to isomorphism bearing a given kernel, okay? And you might also wonder, well, what about the surjectivity condition, right? Because in the first isomorphism theorem, you need a surjectivity for that to work. Well, in our context, everything is surjective. We're basically just or almost like declaring by fiat that everything is surjective. Let me tell you how that works, right? So imagine a polynomial map, like any one of these polynomials that we have here on the screen, right? Is it surjective? Is a polynomial surjective? Well, no, it could be a constant map, right? But I already said we're not talking about constant maps, right? So if I give you a non-constant polynomial, is it surjective, right? I think, well, what about f of x equals x squared? That's not surjective on the real line, right? Yeah, okay, sure. But if you go to the complex plane, then it is surjective, right? And that's a well-known theorem. It's called the fundamental theorem of algebra. Every polynomial has a root over the complex numbers. And you can generalize that. Every polynomial has a root over the algebraic closure of whatever field you're working with. And so if you do that, if you work in the algebraic closure, then every polynomial is surjective. And so then these isogenies must be surjective. And being surjective, the kernel then determines the homomorphism up to isomorphism, all right? And furthermore, Veloux formulas also give you an explicit formula for that isogeny, right? So that if I give you the kernel as a finite subgroup, like it's a finite subgroup, so I can just list the points. I literally give you a list. Here's the points. Here are the points in my finite subgroup. Then Veloux formulas, you run them through this formula and you'll get the equations for that isogeny right here. The equations are right here. You can evaluate everything here. It might not be so clear how to get rational maps out of these, But actually, I don't even think we need that part. We just need that you can evaluate the isogeny. Given an input point, you can calculate the output point. And these equations clearly allow you to do that, right? You're just taking like the x coordinate of p here, or the x coordinate of p plus q, or whatever, where q is the index of summation, whatever. Okay, so you can evaluate the isogeny using these formulas. I say the isogeny because I'm implicitly sort of taking for granted that there's only one, which is not technically true. But there's only one up to isomorphisms. That's the part that's true. Okay. All right. So now with these formulas in mind, I'm going to, declare some notation, right? So I'm going to talk about this E/G or E mod G. I'm going to use that notation to denote the codomain of the isogeny that has the kernel equal to G, right? So this E mod G notation borrows from group theory, right? So in group theory, if we have a subgroup H, we can look at G mod H. Right? It's the same kind of thing. The degree of the isogeny, it turns out in this case, is equal to the number of elements in the kernel. Right? So what do I mean by degree? Well, it's just the degree of the polynomials, right? Except you have to be careful which polynomial, because the polynomials don't all have the same degree. I think we want the degree of that polynomial, F1. Right? So that's the one that we want. Right. The degree is also equal. I mean, it makes sense when you think about polynomials, right? The degree of a polynomial is equal to the number of roots, right? And actually, the number of roots is the same as the size of the kernel, right? You're looking at the things that map to the identity element, right? So the degree of a polynomial is equal to the number of roots. If you know enough abstract algebra, that's not technically true in certain cases. Like you could have an inseparable polynomial and then it wouldn't be true, but I'm just saying, and that could happen here as well. But so I'm oversimplifying a little bit, but in general, the degree of a polynomial is equal to the size of the kernel, which in this case is G, right? Now for cryptography, or more generally for computation, we care about how expensive it is to evaluate this formula. And if you look at the sum, it's a sum over essentially, the number of things in the sum is the size of the kernel, right? Or the degree of the isogeny. So that's how many things you have to add up. And so that's the computational complexity of evaluating these formulas. Now, this was state of the art in 1971. It is now 2022, I guess. And so we know how to do this a little bit better now. If you take the word value, I'll do it over here on the bottom here, and you draw a line over the top, guess what? That looks like a square root sign, okay? And so that's a really cute sort of notational trick that the authors of a paper that unfortunately I haven't cited here, but I could just tell you it's called value square root, right? And so what they did is they found a way to do this using square root operations. Sorry, I got the square root in the wrong place relative to the parentheses, but they were able to improve this time cost to square root of degree instead of just the degree, okay? But in our case, actually, this doesn't matter so much because for SIDH, all of our degrees these degrees are like less than or equal to 3, right? And so that square root savings doesn't actually result in any savings. It gets overwhelmed by the implied constant. But if you're working in other sort of types of crypto systems where you do need to evaluate larger degree isogeny using Value's formula, then you do care about that square root, and that really helps there. Okay. All right. So let's talk about SIDH, how this works. So SIDH is a thing. It's a public key crypto system that I invented along with Luca Di Feo, my postdoc, back in 2011. It uses isogenies between supersingular elliptic curves. Okay, I guess I haven't technically defined what supersingular means. I don't think it matters too much for this talk, but I'll just do it very quickly here. So if we look at the, I'm gonna have to like put this down in order to write on it. So if we look at the endomorphism ring of an elliptic curve, right? Endomorphism meaning the set of all like isogenies from the curve to itself. Now that's a set, of course, but it turns out it's also a ring. You can impose a ring structure on this, where multiplication is composition of isogenies. It turns out that this is isomorphic to either a imaginary quadratic order, so something like integers adjoined to square root, or it's isomorphic to some sort of quaternion algebra. I say quaternion algebra, but I really mean like quaternion order ramified at P in infinity, which is now as a abelian group, the latter structure has rank 4 instead of rank 2. So in the second case, we call this supersingular. All right, so elliptic curves that are supersingular will be those where the endomorphism rank is rank 4 instead of rank 2. The reason why we prefer supersingular elliptic curves is because somehow, well, first of all, there's fewer of them, right? The number of supersingular elliptic curves is P plus 1 over 12 for a given, over FP for a given prime is P plus 1 over 12. So this is this field here is like a field of characteristic P, or in this case, characteristic P squared. Sorry, size P squared, but characteristic P. The number of supersingular curves is finite. The number of like non-supersingular curves, which are ordinary curves, that's very much infinite. There's sort of lots of those because we're working over an algebraic closure. So you can like take larger and larger, field extensions, and you'll get more and more elliptic curves. But with supersingular curves, that doesn't happen. Once you get to FP squared, you have all the supersingular curves you're ever going to have. You don't need to take any more field extensions. And so that number is finite. But somehow, like, the number of isogenies between the supersingular curves, is just as much as the number of isogenies between, the non-supersingular ordinary elliptic curves, but the set of vertices that you can go between is smaller. It's finite, not infinite. And so the graph of supersingular isogenies is richer. It has more structure. And in fact, graph theorists, cared about supersingular elliptic curves long before cryptographers did, because these sort of isogeny graph of supersingular elliptic curves was one of the first known like Ramanujan families of expander graphs satisfying the Ramanujan bound. All right. So what we use in cryptography is the same graph, but we exploit the sort of good expansion properties of this graph to make and design crypto systems that are sort of interesting to break, so to speak. Okay. All right. So in SIDH, what you do is you start out with a supersingular elliptic curve E over a finite field F, which is going to be FP squared is going to have size P squared for some P. And we're going to have Alice and Bob, two parties, and they want to exchange secret messages with each other. But they don't want to have to send anything secret, right? So by sending, the standard thing in cryptography, right? By sending public data, establish a shared secret, all right? And so what we're going to have Alice and Bob do is we're going to have each of them construct an isogeny, right? So Alice is going to choose a kernel, which I call capital A here, and then Alice is going to send this E sub A, this codomain of the respective isogeny to Bob, and Bob is going to do the same thing with his kernel instead of Alice's kernel. So Bob is going to choose a secret kernel, capital B, and then compute the isogeny going from E to E sub B, where the kernel is B. And then Bob is going to send that codomain E sub B over to Alice. All right. And then the shared secret, what that's going to be is it's going to be, imagine if I took the original elliptic curve E, all right, and then I draw this like diagonal isogeny where the kernel is, well, what I want to write here is that the kernel is, no, I didn't want to do that, sorry. What I want to write here is I want to write that the kernel is A union B. Right, that's what I actually want here. But I can't literally take the kernel equal to A union B. Like that doesn't actually work. The reason why that doesn't work is simply because A union B is not a subgroup, right? Like if I take the union of two subgroups, it's not necessarily a subgroup. So I need to take like the smallest subgroup that contains A union B. And so that's the subgroup generated by A and B. So if I do that, then I get a single isogeny, which is then the sort of, it's in some sense a composition. It's not literally a composition. I could call it a composite of phi of A and phi of B. All right, so it's the isogeny that you logically get if you wipe out both of the kernels simultaneously. And it turns out that there are isogenies. We can call them phi like B prime and phi A prime. So I'll write like phi B prime here and phi A prime here. All right, so there are isogenies that you can construct to make this square commutative, to complete this sort of commutative square. All right, and those are the isogenies that we're actually going to compute to find the shared secret. All right, so in particular, Alice, who I will try to underline in red here. It's a little hard to write on the center surface. So Alice is going to compute this map, and then Bob over here is going to compute this map. Right, and so that's how Alice and Bob are going to access the shared secret. Okay. In a little more detail, it goes like this. So we have a prime, and this prime has to be of a special form. It has to be a small prime, like usually it's going to be like 2 times another small prime, typically 3, raised to small powers, right? So I can write like e sub a and e sub b here, minus 1. It has to be a prime of this form. It needs to look like this so that all the isogenies are defined in the proper places, right? If you didn't structure your prime like this, I mean, you could still do it, I think, but your isogenies would need like enormous field extensions in order to compute, and they would be impractical, right? But if you set it up this way, then your primes are going to, then everything's going to be easy to compute, right? So we set our prime to be of this form, and then we take a supersingular elliptic curve, and we have to take a supersingular elliptic curve having a certain number of points, p plus 1 squared points. And this is actually not too hard to arrange. You can just pick, I mean, there are sort of well-known curves, for example, this one, that satisfy this constraint. And for notation, we're going to have to sort of specify what I call a basis of the LA to the EA torsion points and a basis for the LB to the EB torsion points, right? And so what that means is, well, first of all, let's define LA to the EA torsion. So what does that mean? So what that means here is this is the set of all points defined on the elliptic curve, such that, you know, this integer, whatever this power is, this prime power, times p is equal to the identity element. All right, so it's the set of all points that are annihilated by scalar multiplication by LA to the EA, right? And similarly for the other torsion subgroup. Now, it turns out that this is a 2-dimensional subgroup. As an abstract group, it's isomorphic to the product of 2 cyclic groups, right? So it's going to be a product of, it's as a sort of abstract abelian group, it's isomorphic to that product of 2 cyclic groups. And so it's 2-dimensional, and so we just want to pick sort of a pair of generators, right? So being 2-dimensional, that makes sense. And Alice's kernel is going to be a subgroup of this larger group, right? So this being a 2-dimensional group, Alice's kernel is going to be a 1-dimensional, subgroup inside here, right? And to pick a 1-dimensional subgroup, you just need to pick an integer, right? You take PA and then you add in some secret integer times QA, and that will give you that generates a subgroup. Right, so, and that subgroup will be 1-dimensional because you're using 1 generator instead of 2 generators. Okay, and then you're going to compute the respective isogeny, having that kernel. And what you're going to send to Bob is you're actually going to send a little bit more information than just E sub A. Right? You're going to have to send as well the image of your isogeny, the image of Bob's basis under your isogeny. Right. So the P sub B and Q sub B, which are what Bob is going to use to, do his respective half of the key exchange, you have to map them through your isogeny. Now, your isogeny is secret, right? So you can't just send your isogeny to Bob, but you have to give Bob enough information about your isogeny so that Bob can compute the vertical map, right? The this vertical blue arrow, right? And so what you do is you evaluate your isogeny, which is your secret information, on Bob's basis, which is not secret information, and then you can send that information to Bob. And that information doesn't have to be secret, it turns out, at least as far as we know. Maybe it does, and then this whole thing doesn't work, but people have studied this for 10 years and haven't found a problem yet, all right? So you have to send that to Bob. And then once Bob gets that, then Bob takes this, and this, and this, and then computes that respective isogeny, starting from EA, and then having kernel phi A of PB plus SKB phi A of QB. So in other words, starting from EA, you're going down, and what you're doing is you're taking, like, Bob's kernel is B over here, right? And then over here, you're gonna essentially do phi A of B. That's your kernel, all right? And this was actually one of the sort of main, I guess, technical innovations in SIDH, right? Phi sub A of B involves two secrets. It involves Alice's secret, capital A, and Bob's secret, capital B, all right? And yet Bob needs to know this in order to compute that blue downward arrow, right? And so a sticking point for like, I don't know, it took me 8 years to figure this out, right? Like, how do you have people compute, how do you have Bob compute phi A of B without Alice giving A to Bob or Bob giving B to Alice, right? And so the way that we, Luke and I eventually got around this was by having Alice send phi A of the basis to Bob. So there's nothing secret about the basis, right? But then once you know phi A of the basis, you can infer what phi A of your kernel is, because isogenies are linear. So if you know the action on a basis, you know the action on all the points that you care about. Okay. All right. So that is SIDH. I have been asked if I can make this sort of partially interactive. I will see what I can do here. So I guess we'll define a prime first, and it has to be like a power of 2. I don't know if you can see this actually. It might be a little bit too dark. Can you? So
yeah, the blue is a little hard to see.
Okay. Well, I don't
know if it's possible to change it. If it's not, then I guess.
We'll just roll with it. I'll say what I do. P is 2 to the 3 times 3 to the 2 minus 1. All right. So P is 71. Okay. It is indeed a power of 2 times a power of 3 minus 1. And now I want to take a finite field. It has to be FP squared, right? So I need a finite field to be, actually, I think I need a parameter here. So I need this to be a finite field defined of size p squared, and I need a modulus. I think x squared plus 1 will work for this purpose, right? So F is a finite field in I, which is square root of minus 1, of size 71 squared. So it's like complex numbers mod 71 or something like that, okay? And now I need an elliptic curve, like a starting curve. So that's going to be defined over F and having coefficients 1, 0, right? So E is the elliptic curve y squared equals x cubed plus x over finite field in I of size 71 squared. So that's my elliptic curve E, okay? And now I need like, in order to, well, I need, I can just, you know, for now, just pick like a random point on E just to show you, you know, what they look like, right? So there you go. There's a random point on E. Actually, I needed to save that point. So there we go. Here's a random point on E, okay? And I can ask for the order of this random point. In this case, it's 36, all right? And so what that means is that 36 times R is the point on the identity, right? Is the identity point in the group, right? And anything smaller than 36 times R is not the identity point. You know, these are going to be other points, okay? Once I have a point, I can compute the isogeny that annihilates that point, right? So I can compute an isogeny having kernel R, right? Now R is a point, it's not a subgroup. And so what I really mean by that is, I mean, you know, you're taking the subgroup generated by R, okay? And so in this case, I get an isogeny of degree R. If you really want to see what the isogeny looks like, it looks like that. I mean, it's a polynomial of degree 36 with coefficients in like complex numbers mod 71. It's not particularly pretty, right? You know, that's just what it is. But for our purposes, for SIDH, we're going to need points of order like 8 and 9, right? We need a point. We need a like the 2 to the E and 3 to the F torsion. So we would get that by doing something like, you know, we would take, so R has order 36, right? 36 is 4 times 9. So if I take Q to be like 4 times R and so on, then I would get a point Q of order 9, right? And I could do this actually, again, I could do this like all over again, right? I could take, I could just keep doing this, looking for other points. Here R has order 72, right? So now if I took like 8 times R and then I set that equal to like, I should have called this QB. The other one I should call QA. Right. So now QA and QB have order 9, right? And QA and QB are hopefully like linearly independent points. All right. There is actually a way to tell that. You can do something like compute like the Weil pairing, which is a non-degenerate bilinear map. Oh, I need an order. whoa, sorry. Like that, yeah. So I can compute the Weil pairing of QA and QB and just check that it's not 1. If it's not 1, then I know that they're linearly independent, right? No, actually I need more. I need that the order of this is full order, but it is. Okay. So yeah, so now I have my points, and then I can take my isogenies, right? So I can compute an isogeny of, let's say kernel QA plus, okay, here's the interactive part. What secret key do you want? It has to be an integer from 0 to 8.
Three.
There's a chat. Oh, sorry, my chat window's not open.
The 3 and 4 have both been suggested.
Oh, okay. 3 and 4. Actually, we'll do 4. 4 is in the chat. All right, so there you go. That's my isogeny. You'll notice that the codomain is right here. It's y squared equals x cubed plus 47x plus 45. I can compute the rational maps. And to show you what that isogeny looks like. In practice, you would not compute these rational maps directly. You would compute them sort of a factor of 3 at a time, right? Like this isogeny is degree 9. The kernel is a subgroup. It's a cyclic subgroup. Of order 9, you will have a filtration where you have an index 3 size 3 subgroup, and you would go sort of degree 3 isogenies at a time. Okay. All right, I'd like to do more interactive stuff, but I think I'm actually going to run out of time. So that's all the interactivity you get. Sorry about that, but you can make it work. All right, it's been well tested. We all understand. Well, cryptographers at least, we all understand that this works just fine. All right, so there we go. Those are what some of these isogenies look like. Except in practice, of course, they're going to be much bigger. Right? In practice, like just to give you an idea, in the Sykes specification. E sub A is something like, there's one example where we have E sub A is 372 and E sub B is 239. All right, and I actually remember that because 239 is math 239 is something I've taught many times, and so I remember that. Isn't that a prime as well? All right, anyway, so typically these are powers of 300, 400 bits or something like that, right? They're big numbers, all right? And you can't compute them directly. You really have to compute them sort of 1 power at a time, right? So you would compute a composition of 239 3 isogenies instead of computing a single isogeny of degree 3 to the 239 or something like that. All right. And you actually need a big degree for cryptography because otherwise you don't have enough like entropy in your private key. You would just guess the private key. So these degrees have to be big, right? But you can get around that problem. Okay, so why do we care about isogenies? There are many potential reasons why we might care about isogenies. The easiest one to reach for, and therefore the one that we actually use to sell this work, is that quantum computers are coming and they're going to be a thing. And when they do come here, a lot of cryptography that we know today is not going to work anymore. Right? I say a lot, but actually, I think only in public key cryptography is that statement true, right? A lot of the public key cryptography that we use today will not work once quantum computers start existing, right? Like things like RSA or ECC or anything along the lines of you have a group, you're doing arithmetic in the group, and you're trying to make this secure. That kind of stuff is just not going to work because you have like Shor's algorithm that breaks all of this. Right. So for now, we're still okay because we haven't built a quantum computer yet. It's going to take some time to do this. I think when I joined in 2006, I'm not picking on Michele Mosca here, but he was predicting it would happen in 10 years, and it's been more than 10 years, and it hasn't quite happened yet. So we're now predicting that it's going to happen in 10 years, but I don't know. All right, but it is probably going to happen, I think. Progress in these things. Never goes backwards, right? The attacks always get better, the hardware always get better, our knowledge always gets better. Already in 2021, we have things like, I don't know, smartphones and stuff like that we didn't have 40 years ago, right? So what might we have in 40 years? It's not a stretch to think that we might have quantum computers. All right. So once we get quantum computers, we're going to need like different cryptography as far as public key cryptography goes, right? So public key is anything where you are trying to communicate in secret, but without sending any information that is actually secret, right? So where you send information that like implies a secret, like in this case, sending an isogeny, which implies a secret kernel, but you're not actually sending the secret, right? so these kinds of things are going to, well, the ones that the public key crypto systems that we use today, it's mostly ECC, elliptic curve cryptography. Actually, I think it's like 90% of what we use on the internet is elliptic curve cryptography. Most of that is going to break when we start having quantum computers, and so we need what we call like post-quantum public key cryptographies. In other words, public key crypto systems that would still be secure even if somebody was trying to attack you and that person had a quantum computer at their disposal, right? And nowadays we recognize 5 major families of post-quantum public key crypto systems. I have them right here: lattice-based, code-based, multivariate, hash-based, and isogeny-based. And that last one, isogeny-based, you know, is something that I played a role in making into an element of this list, I guess, before my work. You know, I think even if you go back to like, you know, PQ crypto, like, I don't know, 2007 or whatever the first post-quantum cryptography conference was, and you look at their call for papers, they didn't mention isogeny-based cryptography, but now they do, because now we have isogeny-based crypto systems, right? So here's a sort of brief history of public key crypto systems and how they look like and how they work. So in the beginning, we had Diffie-Hellman, which is, so the word SIDH stands for supersingular isogeny Diffie-Hellman. The DH is inspired by Diffie-Hellman. So Diffie-Hellman sort of it's 2 people with Diffie and Martin Hellman. They were the 2 people who first invented the concept of public key cryptography, right? And their particular crypto system used discrete logarithms in a finite field, right? So reversing sort of the exponentiation map in the finite field. And then very shortly thereafter, RSA was a very famous crypto system. That's 3 people, Ravesh, Shamir, and Adelman. They invented an actual public key crypto system, right? Diffie-Hellman had invented the concept of public key cryptography, but they didn't invent an actual system. That was left to RSA to do, all right? There was a sort of span of time where most of the public key crypto systems that people cared about were all based on either Diffie-Hellman or RSA. Although if you look closely at the dates here, technically code-based cryptography does make an appearance on this list in 1979. That was invented by Michaelis. Now 1979 is not too far apart from 1976 and 1977, but actually code-based cryptography was ignored for a long time. It isn't until sort of recently, with interest in post-quantum cryptography, that code-based cryptography has been sort of revived as a discipline. The reason for that is pretty simple. I think the Michaelis crypto system requires enormous public keys, right? Like you need 1 megabyte public keys to make that work. And 1 megabyte doesn't sound like a lot right now, but in 1979, that was a lot, all right? Like you couldn't fit that on a hard drive even, right? So yeah, so for a long time, all we had was basically Diffie-Hellman, RSA, and their, like, I would say, derivatives and variants, right? So things like elliptic curve cryptography or pairings or composite residuosity. And all of those are based on discrete logarithms and factoring integers, right? So these 2 problems, and these 2 problems here just happen to be the exact 2 problems that quantum computers are really good at solving, all right? So that's why when Shor's algorithm came out in 1994, there was not exactly a sense of alarm, but a realization that we probably need to move to other stuff pretty soon if quantum computers are going to be a thing, right? And then later, some other crypto systems came about, right? So here I'm only talking about the encryption schemes, right? Notice I have the word encryption here in the title of this slide, right? There's actually 5 families of public key, sort of post-quantum public key crypto system. 2 of them are predominantly only used for signatures. I'm only talking about encryption, so these red ones right here, right? So when it comes to encryption, there's not much left, right? There's sort of lattice-based schemes, which were first formulated in 1996. There's the isogeny-based schemes. Now, these were first formulated also in 1996, although not published until 2006. There's a small story behind that. And now, and if you're just looking at broad categories, that's it, right? Like at this level of resolution, there's not really very much on this list, right? I tell people, like my students that when you're looking at broad families of public key crypto systems, like in terms of, especially when you categorize them in terms of like the mathematical problems that they depend on, it's a very small list. It's not more than a handful, right? It's either one handful or two handfuls, depending on whether you count the right column here or the left column here. But it's really not very much, right? And we have lots of public key crypto systems, but they're all based on these these primitives, right? These are basically pretty much all the primitives that we have. Now, okay, maybe like some cryptographers might complain, oh, you left out like group-based cryptography or something like that. Yeah, okay. There are some, but yeah, like group-based cryptography, I'm gonna maybe go out on a limb and say those have not been exactly very successful today, and most of the schemes that have been put out have been broken in some way or another, right? So speaking of the schemes that have survived in a certain sense, and when I say survived, of course, I'm being a little biased here. I've picked the survival threshold to be sort of just below where SIDH is, so that SIDH makes it onto this list, right? So yeah, you can call me biased, but I think it's fairly reasonable to say that it's a big contribution to find a new problem that we can base a public key crypto system on. It's not easy to do that, right? And so we really care about this problem, right? Not just sort of from the point of view of like cryptography and trying to hack it or break the crypto system in some way, but because it is one of the few problems that does have an application in cryptography, we want to understand sort of the mathematical structure of this problem and how it relates to the other problems. Okay, and so that's going to be like what I'm going to talk about in the rest of my talk. So I see that I'm actually running out of time here, so I'm going to skip some slides. I just skipped a slide. All right. What about the attacks against SIDH, right? So how do you actually attack this? If you're trying to understand how easy it is to break the scheme, or how easy it is to solve this problem, or how hard it is, you want to understand sort of at least what the fastest currently known attack is. All right. And so on this slide, I have a sort of depiction of the how you would go about attacking SIDH. The way to do this is what you do is you form a graph, right, where the vertices are elliptic curves and where the edges are isogenies of a fixed degree, in this case degree 2, between elliptic curves. So each edge here is an isogeny of degree 2. All right. Now, I don't know if you sort of are I don't know how closely you're paying attention to If you are paying attention, you might notice that isogenies technically have a direction. An isogeny is a function, and so it is a directed map. And so actually this should be a directed graph. But we normally like fuzz this out and make it undirected because if you have an isogeny, you have like a dual isogeny, which like goes the other way. So it just goes backwards in the reverse direction of the original isogeny. All right. And to a like 99.9999909% approximation, you can treat this graph as undirected. All right. There are some very small exceptions where you can't, but it doesn't matter for our purposes. So undirected graph, yay. All you have to do is you have to start from your known endpoints, right? So your endpoints are going to be E, which that's the starting curve, and then EA, which is the public key, that's the codomain, that you also know. And you're going to like brute force an isogeny of degree 2 to the E. So they have to be like, so the length of this has to be 2 to the E. And each edge has degree 2, so you need E edges. And E is, remember, something like 370 or something like that, right? So you need to find, a path of length 370 from this vertex to that vertex on this graph, all right? That's much easier said than done. This graph has, something like, well, P plus 1 over 12, 2 to the 500 or more vertices, all right? And it has really good expansion properties. It also has large girth, although I can't prove that right here. But so it has lots of graph theoretic properties that make it sort of more or less pretty hard to do this. The best way to do this that we know of is to just take, sort of trees on both sides until you meet in the middle. And that takes like square root of, square root of 2 to the E time or something like that. If you have a quantum computer, you might be able to reduce that to cube root of 2 to the E, right? So those are the attacks. Now, it turns out that there is also sort of a cryptographic attack that you can implement against this. This is the so-called Galbraith Pentatonic G attack, or GPST attack. How this attack works is, let's say Bob is acting maliciously and Bob wants to determine Alice's private key. All right. So normally Bob would send a public key and it would look like this, all right? It would look like that information. But what if instead Bob sends a public key and it looks like that, all right, where Q is chosen to maximize mischief, right? And so what Bob is going to do is Bob is going to choose a point Q such that 2 times Q is equal to the identity, right? So Bob is just going to choose a point of order 2 and add this point in, right? And then send this result to Alice. Now you might think, oh, well, you're sending a bogus key. Alice is going to get garbage, right? The problem is that that's not true in this case where Q is chosen to maximize mischief. Because if you choose Q so that 2Q is the identity, then notice that Q in Alice's computation is being multiplied by Alice's secret key. So if Alice's secret key is even, 2 times Q is the identity, even times Q goes away. And so it's as if Q is not there. And so Alice will actually get the correct answer. And you might think, oh, that's great, Alice gets the correct answer. But no, actually, it's very bad. You don't want Alice to get the correct answer here. You want the protocol to screw up, because if it doesn't screw up, then that gives Bob some information. That tells Bob that Alice's secret key is even, right? And oh no, that's a big problem. Now Bob knows like literally one bit of information about Alice's key, right? And if you're not trained in cryptography, that doesn't sound like a big deal. People who are trained in cryptography know that this is a really big deal, because once you know one bit, then the floodgates are open. Sort of, you can manipulate with knowledge of that bit. You can then send a second, smart, intelligently chosen Q to figure out what the next bit is, and so on, all the way up the line. You can in fact figure out all the bits this way. Okay. So in order to prevent this attack, we actually have to do things like there are like countermeasures we have to do. One of them is called Fujisaki Okamoto. It works perfectly fine, but it like doubles the computational cost of the protocol, right? So there are things you have to do, right? And the reason I point this out is because this is relevant for sort of the mathematical sort of questions that I wanted to talk about, right? So if we look at the math problems that one would encounter in the course of studying SIDH, they're going to be something along the lines of these kinds of problems, right? So for example, the isogeny problem, right? Given a public key for Alice's, isogeny, something like this, right? So given this public key, find the secret key, which is the A, right? Find the kernel, right? That's a very natural problem to ask, right? I mean, if this problem can be solved easily, then SIDH is certainly insecure, right? You don't want to be able to find the secret key given the public key, okay? But there's other problems that you can also formulate, right? Like, for example, it's not actually necessary for an attacker to find a private key. All that they would need to find in order to break the crypto system is they just need to find the shared secret that you use, right? So the sort of piece of data that Alice and Bob eventually compute that they use for their, for their real encryption, right? And so that shared secret, like the common secret that they both compute but never have to send, all you have to do is compute that, right? So then that gives you this problem. Given 2 public keys, find the corresponding shared secret. Can you do that, right? And then in some cases, you might not, care about having 2 inputs. You might just care about 1 input, right? So given 1 public key, for a fixed, Alice public key, can I construct a function that takes, a arbitrary Bob public key and then finds the shared secret, something like that, right? So that we can call one-sided SIDH, right? That's the kind of problem that you might care about if you're designing a public key crypto system as opposed to a key exchange, okay? And then all of these problems have like decisional variance, right? So for example, given, let's talk about 2-sided SIDH, right? Given 2 public keys, find the shared secret, right? So then the decisional variant is given 2 public keys and a 3rd object, is that 3rd object the shared secret? Can you even tell if you get a correct answer? Can you even tell that your answer is correct? And so these kinds of problems also come up, okay? And it turns out that there are some relations among these problems. Some relations were already known, right? So for example, there's what we call a search to decision reduction, or maybe I got that backwards. I don't think I did, but it's a search decision equivalence, right? It turns out that the search problems and the sort of decision problems are more or less equivalent. Let's for concreteness, let's just take like the isogeny problem here, right? So given a public key, find the corresponding secret key, right? And then the decisional problem here would be given a purported public key, is this public key actually a valid public key, right? Now notice that this is exactly the problem that you're faced with in the GPST attack, right? You're given this public key, in this case, the second arrow, the one closer to the middle of the slide. And if you could tell that that was a illegitimate public key, then this attack would be foiled, right? If you could tell that that third component was manipulated, then you could simply avoid doing the key exchange and never give away information about your key, right? So that's the problem that you want to sort of solve in order to avoid that kind of attack. In a lot of crypto systems, this kind of problem is very easy to solve. Like for example, in it's not so easy in RSA, but in discrete logs, it's very easy to solve, right? Like, given an integer is an integer mod p, well, duh, of course it is, right? But here, it's not so easy to solve this problem, right? Given a public key, which now is a triplet of, a curve and 2 points, is this a valid public key? We don't know, right? And in fact, Galbraith and Vercaterin showed that if you could solve this decisional problem, then you could just break SIDH, right? You just sort of solve the problem to begin with. How do you do that? Here's how to do that. Let's say I have a now valid public key and I want to break SIDH. I want to just find the private key, okay? So how do I do this? I compute 3 different 2 isogenies, right? Now, one of these will lie on the correct path, right? Like somewhere in here, there's a correct path. I should probably use a different color for the correct path, right? So somewhere in here, there exists a correct path, right? And that correct path will pass through one of these 3 arrows, but not all 3 of them. It'll pass through one of these 3 arrows. And all you have to do is figure out which arrow lies on the correct path. If you can do that, then by induction, you can find the correct path just by backtracing all the arrows that lie on the correct path, right? And so what you're going to do is for each of these, candidate correct paths, you're going to compute all the isogenies that you could have. Actually, there's there, right? So those are all 3 isogenies that you could have, right? And similarly for the similarly for the incorrect paths, which I would denote in like purple, right? So something like this, this, and this, or something like that, right? And the point is, you can tell when you're on the correct path because the correct path will have one other vertex, in this case, this vertex, that satisfies the decisional problem, and the incorrect paths will not, right? The correct path will have 2 vertices that satisfy the decisional problem. The incorrect paths will only have 1 vertex that satisfies the decisional problem, right? So now you can tell, using a magic algorithm to solve the decisional problem, you can tell which arrow lies on the correct path, and then by induction you can tell what the whole path is, right? So things like that were already known.
David, if you could finish up in the next minute or 2, that would leave time for questions then.
Okay, I can do that. But what we wanted to do was sort of generalize and extend this, right? So we did that, right? And so what we did was we, considered all, the different types of oracles that we could think of, right? All the different types of things that you could solve, like, if you could solve this, could you solve it? If you could solve that, could you solve this? We made a big list of them. We organized them into a nice sort of pretty picture, and we proved that these are all equivalent. Now, not all these proofs are the same. These proofs are, some of these are trivial, like some of these are very obvious. Some of these are quite involved. They you need like intersection theory or cohomology or things like that, right? But my student and I, well, let's be fair, mostly my student, because that's why he's the first author on this paper, proved that these are all equivalent. And so, and some, there's all these computational problems, all these decisional problems, and they're all the same, right? So that they're all sort of equivalent to each other, more or less. And specifically, I think the most important consequence of this work is that, one consequence is that you can't validate public keys. Now, this is, strictly speaking, this is not a consequence of our work because Galbraith and Vercaterin had already shown this, but we showed it a different way. The most important consequence that comes out of our work is the second conclusion over here. There's no such thing as a gap Diffie-Hellman problem in this case. There's no way to have a sort of situation where you can solve the decisional version of SIDH, but you can't solve the computational version, right? And so what that implies is, now, cryptographers will recognize what this means, right? All of pairing-based cryptography, right? There's this entire rich area of cryptography that is used to design all sorts of advanced functionality. All of that is based on gap SIDH, right? And so what this is saying is that any sort of functionality along those lines is not going to be possible with SIDH, that you're going to need to do something else, okay? So maybe in some sense a negative result, but at the same time something that's important to get out there because I've actually seen papers where this problem has been gap SIDH has been proposed as a basis for constructing crypto systems, and it's important to put out there that no, you can't do this. There's no possible way to do this because these problems are equivalent. Okay. All right, so that's it. I've been requested to stop, and I'm going to stop. Thank you.
Great. Let's unmute and thank David for his nice talk. Questions? So I guess I just have not really necessarily a question about the research, but it's kind of an interesting situation where you're applying to make this a standard. That's not something that many of us will have experience with. So what is that like? And does that change the way when you're publishing a paper, you structure your arguments or anything like that?
So the standard business it's a funny business. I mean, when you're publishing papers, what you care about are oh wow, that's a great idea. That's something that I would never have thought of, or wow, that's a real advance, or that's a true innovation, something like that. You're looking for these sort of almost like jewels of an argument where it just your cleverness, I guess, really shines or something like that. But when you're writing a standard, they don't care about that. What you need in order to sort of get something standardized is you have to describe to non-mathematicians in the minutest detail exactly how to do every single little, like, I don't know, like even like bit operation, or how do you represent field elements at the byte level, blah blah blah. It's just there's all this like almost busy work, I guess, that you just don't run into in a math paper. That's just like to get in at the ground floor, right? And then the process of like having a competitive process for deciding a standard is something that I think not many people do get to experience. There's just aren't that many situations where there's an open competition for a standard. Now, I know that NIST does not like to call their process a competition, so it is a non-competition. But still, like, there was no competitive process for, like, I don't know, SMTP or DNS or something like that, right? Those just sort of became standards because that was what people were using, and it kind of shows, to be honest. But when you do have a competitive process or a non-competition process, then then there's like, I don't know, like certain like political elements get thrown into the open here, and they can, in many cases, they can even like overwhelm the technical arguments. It's not exactly a fun process, but it is something that I'm enjoying in a certain sense because I know that not many people get to do it, and it's not like it is a personal risk to me to do this. It's not anything like that. It's something that I can just go, oh, that's interesting, that this is how that kind of process works. That's an interesting sort of personal attack that you couched there in some technical language or something like that. So those kinds of things, I don't participate in them so much, and I'd like to think actually that I've developed a reputation of being cool enough that when I do participate, it means that something's really wrong. But that's been my take on this whole thing.
Great, yeah, it's very interesting, something that we won't get to experience really. There's a question in the chat here from Chelsea Comlo, which says, do any of the other PQ constructions allow for a gap assumption, or is that lack thereof in SIDH similar to other schemes based on lattices, etc.?
Is there anything else that allows for a gap assumption? I don't think so. You could take lattices and make like full-blown indistinguishability obfuscation and then construct whatever you want out of that. But I don't think that's the answer you were looking for. That's like much less efficient than a direct gap assumption. I really don't think so, but I'd have to actually check, because lattices are not my thing. Maybe there is a gap lattice assumption somewhere, but I would be surprised if there is, because in a lot of lattice-based crypto systems, there is the same kind of thing. There's a search to decision equivalence. And whenever there's a search to decision equivalence, that means the two are equivalent and you can't have a gap.
Okay, any other questions?
Kind of on a similar question, do you know if any of these results have been translated over to the Seaside setting?
Seaside, okay. Well, some of them do not translate. For example, you can directly validate Seaside keys. In fact, Seaside, the reference implementation comes with a function that does just that in their code. Whether or not you can have some sort of gap or not between like computational Seaside and decisional Seaside, that, you know what, there was a paper out there that sort of broke decisional Seaside in the same way that, you know how decisional DDH is, decisional like normal DDH is broken in the case where you have, where the base value is a generator of a finite field. You can break DDH in the sense that because you can tell quadratic residuosity, you can tell the parity of the exponent, and that breaks DDH, all right? And the same kind of thing actually happens with Seaside. You can tell, like, Seaside often works with a cyclic class group, right? And using a much more complicated construction than just quadratic residuosity. But it's the same kind of thing, actually. It's like some sort of reciprocity on some algebraic geometry construction. You can tell the exponent, the parity of the exponent in Seaside. So you could avoid that by using like a prime order subgroup inside Seaside or something like that. But like raw, Seaside using the full, class group and a generator on the class group, decisional Seaside is broken. I don't remember exactly where the reference is, but I have seen it on ePrint.
Cool, thanks.
Anyone else?
I have a follow-up question, more for David's point of view on Seaside. Like today, how confident are you in the results, like claim security results on Seaside?
Okay, so that was largely the slide I skipped, right? Where is that? Seaside. Seaside is this alternative proposal. It's newer than SIDH 2018. It uses like, it has this advantage that, well, the main advantage I think is that you could directly validate keys, right? So as I just said, so we can't actively attack it as far as we know. The original Seaside claimed sort of 512-bit public keys, right? Something like that. But it is now believed, in light of like Pikert's work and things like that, that we're going to need at least like 4,000 bits, maybe 6,000 bits to make Seaside actually work. And if you look at sort of Seaside using, let's say, 4,000 bits, it's going to be much slower than SIDH, right? Like this 50 milliseconds is assuming 512-bit keys. But if we believe, see, the security analysis it's hard to pin down the security analysis because we don't have quantum computers. So we don't know exactly how good a quantum computer will be at breaking these things. But based on our, I would say, current understanding, 512 bits is not going to be enough. You're going to need something like 4,000 bits to achieve real practical security against what we think are going to be quantum computers. And so with 4,000-bit public keys, Seaside is going to take, even if you double the key size to 1,000 bits, it takes like a second or so. It's really slow. And then if you go up to 4,000 bits, it's going to be much slower. You're not talking milliseconds anymore. it's going to be much slower. And then the keys aren't even going to be bigger, smaller. That was the main advantage of Seaside, other than the direct key validation, was that, well, hey, 512-bit keys, those are really small. Those are even smaller than SIDH, right? Which already is smaller than anything else post-quantum, right? But if you have to go up to 4,000 bits, then it's not smaller than SIDH anymore. So in that case, the only advantage of Seaside as a key exchange is that you can directly validate keys. Now it turns out that Seaside is interesting for other reasons than key exchange. In Seaside, you can make protocols that require some amount of algebraic operations, like group operations, because Seaside does have a group. It's not exactly a group; it's a group action, but there is a group involved, right? Some people have claimed that SIDH also has a similar group action, but that action is not very accessible. It takes a long time to compute. Like it would only make sense to compute that group action in the context of an attack. But with Seaside, the user computes the group action. And so there's a group that you can use for, like, if you need to, like, I don't know, just as a very simple example, do like secret sharing or something like that, then Seaside would be much easier to do that with than SIDH.
Okay, just for time, I think we'll end the official portion here. So let's thank David again.
All right, thanks.
And anyone who wants to, feel free to stick around.